Hello, dear students. Okay, so this little video is to go over the abstract and to finalize it and show you once again, just to review where the data is coming from with StatCrunch. All right. And before that, I just want to reiterate what the parsing of the data, the parsing of the data on the four different categories that we're going to use above the densities above and below 200 and the densities above and below 1000. All right, so let me go to the Excel for a moment. And here is the full density distribution, meaning that this is for the 230 countries. And it gave us what is known as a power distribution or power law, which I spoke about in the last video. I just want to show you now how to do the trend line so that you can see where the power actually comes from. So if you go to the graph on the points themselves here and right click, all right, any one of those points, you right click and you go to Format Data Series and you open that. Sorry, let's go back here, right click. Sorry, the one above it, add trend line, okay? And then you have to choose here. So here is where it's very informative because you can start with exponential and you see that the trend line is the black. And while I'm here, let me format that a little better so that you can see it better. Let's go to a red color, all right, and a thicker width. You can see that the red line is getting thicker. I've gone to 4 points on the width of the trend line, and it is in red, as you can see here. All right, so again, that was from the little bucket here, which is formatting the trend line. All right, now let's go back to the trend line itself. Here we go. All right, this icon that shows the graph, 3 bars on a graph, this gets us back to the options. If we choose exponential, you see that it doesn't have, there is a slight curving, but it doesn't pick up the values above 1000, which are all those dozen countries that have a density above 1000 persons per square kilometer, okay? It doesn't pick them up. It doesn't define, the red line doesn't define well the countries with highest density. The idea is that the trend line should be the best fit of a curve on our data, which is in blue, all right? The data points in blue connected by a line. So we try linear, it's gonna be even worse because linear is just straight, you see? It's not a very good fit at all. Again, the persons per, not only the value of 150, so linear is not a good fit either. Let's try logarithmic. All right, logarithmic is a little better fit, but still not too good. As you can see, it only goes up to 5,000 people per square kilometer and leaves out the upper 1, 2, 3, 4, 5, the upper 5 countries out of the dozen, so half of the high density countries are not represented by a logarithmic scale. If we try polynomial, again, it's bending and not fitting very well on the curve, on our data points. You can raise the order of magnitudes on the polynomial and see if it gives you a better fit, but it doesn't really. Up to 6 orders of magnitude on the polynomial, it doesn't really give you a better fit, as you can see. And so we continue. Let's look at the power. See, now the power law, or the power trend line, is really the best fit. The tail is totally included within the power description, and then it curves slightly off the data point curves, but then it gets very close to the upper values, all right? And so far, this power curve, this power trend line, is the best fit to our data sets, to our data points, which are in blue, all right? There's one last one to try, which is a moving average, this one. And the moving average also has a better fit, actually, as you can see here, because this moving average line is adjusting as it goes up. However, it doesn't include the last data points here, anything above 14,000 people per square kilometer is not included in that moving average, okay? So it's leaving some of the data out. Now you can increase the period here, and you can see that if you increase the period, actually, the curve diminishes, the trend line diminishes, and it's leaving out more data points, all right, up to a period of 8, 9, and now the curve is actually getting off the data points. So by increasing the periodicity of the moving average, it doesn't help. So we actually need to decrease the periodicity, and then the curve gets better. But if we decrease it all the way down to only 2, which is the minimum, you see that it's leaving some data points out. Like I said, any density that is above 14,000 people per square kilometer is not included in that trend line. So it's not as complete as the power distribution. You can see now picks up all the data points, and even though it's a little off to the side, but still it describes basically the same shape, Keep in mind that the data points, which are in blue, is experimental. It's the actual numbers, and you never are going to have, you would need a very homogeneous distribution, but these are actual numbers of people per square kilometer for each country. So we cannot expect that to be totally homogeneous and fit perfectly on the power distribution. But what I want to say is that the power trend line seems to be the one that best represents the data, that picks up most of the data points on the data and actually bends the way the data is bending here, okay? So that's how we determined that it was a power distribution, a power law, that obeys a power law. All right, then as we parse the data into above and below 200 of density, right? And then also above and below 1,000, this is what I wanted to put out. This is the density, it's already plotted. It's for density above 200. So you can see that if the trend line, now it's backwards, I'm sorry, the trend line is in black and the data points are actually in red. Okay, well, I think we can change that. Anyway, that's the way I did it earlier, so I'm just going to leave it that way. But basically, let's make this a little bigger so you can see what I'm talking about. Here we go. See, The data now is in red. It doesn't matter. You can color these as I showed you with whatever color you want and whatever width you want. So the data is in red in this case, and the trend line is in black. Pause for a moment because I need to. Excuse me. I'm sorry. Okay. So there we go. See, this is the density above 200. Okay, and it shows the 70 countries, more or less, 1/3 of the countries that have a density above 200 persons per square kilometer. And so a power law fits very nicely there. However, when we look at the densities below 200 persons per square kilometers, which is about 160 countries, all right, about 2/3 of the countries of the world, then we see that the best fit is actually a linear plot, which is the linear trend line, again in black, as you can see here, is the best fit. Our data is in red, okay? And the best trend line in this case is actually linear. And that's why the distinction, that's why we chose this margin or this boundary, if you will, the boundary of above or below 200, because of densities above 200 obey a power law distribution, all right? But densities below 200 obey more of a linear distribution, as you can see with the black line here, that is just straight, all right? And so that's why we chose 200 to make a distinction between the two ways that the data is behaving. And the other one was also informative, which was the one for above or below 1,000. And here I was just doing different densities, looking at how the data was fitting to the trend line. I can see when we use below 5,000, for example, is still a power law distribution. Below 2,000, again, is still a power law distribution. But by the time we get to below 1,000, it's starting to curve more. Let's go to trend line here. Okay. It's more logarithmic. As you can see, the fit is a very good logarithmic fit, all right? And so that's why, again, I chose 1,000 above or below 1,000, because again, above 1,000 is going to be the power distribution, but below 1,000, it's a logarithmic distribution, as you can see here very nicely with the black red line. Let me make this a little bigger so you can see it. Okay, so again, the blue is our data, and the black line, the little black line, is the trend line, which in this case is following a logarithmic distribution. So that's the reason for the 4 different types of cutoff or boundaries: above or below 200 and above or below 1,000. Now, finally, to look at the data StatCrunch to see how we came up with these results. Let's go back here to StatCrunch for a moment. Okay. While that loads up, I'm going to point out on the abstract, the first correlation that we looked at was between infected people and diseased people. And the intuition is to expect a strong correlation between these two, between infected people and disease, because the disease were infected, they come from this larger group of infected people, right, confirmed infections, and these are disease from the COVID virus. So we would expect a strong correlation there, and in fact, when we look at it in StatCrunch, I think I delayed too long and they kicked me out. There we go. So I have to do them again. All right. So regression, linear. This is with the full data. So we're using on the x-axis the infected, which is a larger number, right? And the y-axis is the deceased, because the deceased are contingent on the infected, right? In other words, the deceased were infected first before they died. And we see that it gives us a strong correlation of 0.93. Okay. So our claim here that strong correlation between infected and diseased. All right. Then when we compare densities to infected or diseased, we did not get a strong correlation. So let's go back there for a moment. And here is, oh, sorry, I needed to be back in this window. Yes, so we're going to do regression of density to infected and density to deceased. So density to infected. You see, it gives a very poor correlation. In fact, it's slightly negative, but the value is so low, 0.036, that is not significant. So that negative is not even significant in the sense that there's essentially no correlation between the number of infected and the population density as such. Okay, then when we do the other analysis of density to number of deceased, remember from the little table, we get the same result, very poor, no correlation actually. It's also negative, but it's not that informative because it's 0.041, which is essentially no correlation, right? Then when we look at the below 200, oh, I guess it erased all my, I had done this calculation prior, so I would have it already, but I delayed too much and it kicked me out. All right, so I have to redo them here. Now we're gonna do total population, or I'm sorry, population of below 200 density versus infected, okay? And now we get a correlation of 0.23. This is of below 200. So not a very strong correlation between population and infected, all right? And when we look at deceased, the same. Here in the x-axis, again, population, the absolute number of people versus deceased in absolute numbers also. You see 0.27, so 0.23 and 0.27 are really very poor correlation, right? So there's a poor correlation of low density countries, and that's why we state here. Densities below 200 gave poor correlations, all right, of both infected and deceased. And I just show you the StatCrunch data for that. Now let's look at densities above 200 because they gave strong correlation of infected and moderate correlation for deceased. All right, so let's look at that correlation above 200. That's this other window here. All right, so correlations above 200. Again, population, total number of population versus total number of infected gives a strong correlation, 0.96, 0.96, okay? And then we do correlation of population in absolute numbers with deceased. And we do get a correlation, not as strong, but we also get a correlation 0.5, 0.53, all right? So 0.53. All right, then next, the last one that we need to do is above and below 1,000. And you'll see that for below 1,000, it's going to match essentially the results of below 200. All right, so we look at population versus infected. This is for below 1,000. You see, 0.348, 0.348. So 0.35. It's not a very significant correlation. And for the deceased, no, not density, population in absolute numbers, and deceased, 0.311. So about the same, which is not a significant correlation, all right, 0.311. So it's the same, similar to the values of below 200. If you remember, they were like 0.24 and 0.27, something like that, okay? And now finally, when we look at the densities above 1,000, then we get strong correlations on both. Just to show you the data, here we go, above 1,000, okay? So we go to regression, simple. Population in absolute numbers and disease, infected first. Okay, 0.96, 0.969, all right. And then population versus disease, last one. Again, in absolute numbers. Also very strong, 0.998, okay? Which means that then for very high density countries, it does show up that there is a very strong correlation both of infected and of diseased with densities, population densities of 1,000 persons per square kilometer or above, all the way up to Monaco, which has about 19,000 persons per square kilometer, right? And that is the result here. So densities below 1,000 gave poor correlations, but densities above 1,000 gave strong correlations of both infected and deceased, right? Strong correlations of both infected and deceased. So finally, the results then, to put it all together, it suggests that lower density nations, infections and death rates may be more influenced by the way a population behaves during the pandemic, the way a population behaves during the pandemic, more than by its density. This is for low density countries, either below 1,000 or below 200. But for high density countries, the converse or the opposite may be true, all right? For high density, the opposite may be true. In other words, they may be more influenced by the actual density of the population than the behavior, the particular behavior that they're exhibiting during the pandemic. And then finally, the last sentence here is that future studies should try to zero in into each country, because these are densities, these are population densities at the level of the whole country. However, we cannot expect whole countries to be homogeneous in their population. Rather, the distribution is going to be heterogeneous, meaning that typically people cluster in large cities, large urban areas, and therefore the suggestion to look at these correlation coefficients again at the level of state or region. The level of states, for example, in the United States, the 50 states, to go state by state, see? Other countries, instead of states, they have regions, right? And so that's the suggestion, to go into greater detail each country of the world, to look at, so essentially do the same study at the level of each country, okay? And that's the suggestion here, so that then the countries can adjust their behavior according to the density. It may require a different strategy in high density areas or low density areas. And that's what I mean with the specific healthcare intervention modalities. See? By figuring this out and see, first of all, if the power law still applies to these limits at the level of each individual country, 1,000 more or less, above or below 1,000 and above or below 200. And if those values still hold, then look at different modalities on high density states versus low density states. Okay, that's for future studies, which is essentially repeating this study, but at the level of each country, each one of the 230 countries, or at least the ones that have a larger population overall of the world, okay? All right, so that's it then. I'm going to turn this into YouTube and send it to you, and that way you have the explanation of the abstract itself, which, like I say, is a combined abstract of the whole study, whereas for the MDC students, because they require individual abstracts, then I just used above or below 200, which was to make a distinction between the two abstracts for each individual student. But as far as St. Thomas University is concerned, we put all 5 students on the abstract that we use at St. Thomas, all right, which is this one. And what I'll do is I'll send you this abstract also when I send you the YouTube of this email, so that you can compare it. You already have the StatCrunch analysis from the previous video with the little table that I sent you also in in an Excel spreadsheet. Okay, thanks again, and we'll be in touch. The next thing would be then to develop the poster, and we'll be using essentially the figures and the description of the whole project and the figures and the tables from Excel and for StatCrunch for our poster, okay? All right, thanks again, and let me close this section so that I can make a YouTube out of it. Bye-bye now.